Heat, like we say, you hear some people say, I feel heat, I'm feeling heat. So what is heat? Heat, what is the difference? Let's draw a line of dichotomy between heat and temperature. We already said temperature is a measure of the degree of hotness or coldness of a body. So what is heat? Heat is a form of energy that flows from one place to another as a result of temperature gradient. So what are the SI units of heat? We have the calorie, we have the joule, and we have the British thermal unit. So we have that 1 calorie equal to 4.186 joules. We have the 1 BTU. BTU is British thermal unit, equal to 252 calories, and it is equal to 1055 joules. So to that effect, we said heat is a form of energy that flows from one place to another as a result of temperature difference. So to that effect, what is heat capacity? Heat capacity of a substance is defined as the heat energy required to raise a unit mass, to raise the temperature of the substance by 1 degree. So to that effect, we define heat capacity, which is already defined. We say H equal to mc. What is m? M is the mass, and c is a value that we call the specific heat capacity. So the SI unit of heat capacity, which is written as Q in some text, is joules per Kelvin. Joules per Kelvin. So to that effect, let's draw a line of dichotomy between heat capacity and specific heat capacity. The specific heat capacity of a substance is defined as the heat energy required to raise a unit mass of the substance by 1 degree Celsius. A unit mass of the substance is the same thing as 1 kilogram. So to that effect, the specific heat capacity, the SI unit, is joules per kilogram per Kelvin. Let's explain this. Joules per kilogram per Kelvin. It means joules divided by kilogram divided by Kelvin. So which is the same thing as joules divided by kilogram over Kelvin, which gives us joules times K over kilogram. So we can write it as joules per kilogram per Kelvin. And so that is why it is either written like this or like this, that is for the specific heat capacity. So an experiment was performed with a calorimeter. So a calorimeter is an apparatus that we use to perform specific heat capacity experiment. For the exigencies of time, we won't be able to do that. So this is an example, a typical example of a calorimeter. I think the electrical one, this is the negative, this is the positive, this is the stirrer, and it is used to perform experiment when it is lagged. So that's that about the calorimeter. So the basic principle of calculation in our calorimeter is this. We have a calorimeter here which is lagged. What is lagging? Lagging is preventing heat from running away. So when you lag, you can lag with anything that will not conduct heat, like your cotton wool, any other thing that will not conduct heat. So we have the stirrer here, and we have the liquid. So to that effect, we have a solid here that we heat to drop inside the calorimeter so that we can know the temperature of the mixture. So to that effect, the basic idea of the calculation is that the heat lost equals the heat gained. And that's the basic idea we're going to use. So if heat lost equals to the heat gain, and we already said that the specific heat capacity H or Q equal to mc theta, which is mc change in theta, that is theta, MC, change in theta, which is the expression for the specific heat capacity. And we already said that the heat lost equal to the heat gained. So to that effect, there are three temperatures. We have theta 1, we have theta 2, and we have theta 3. So what is theta 1? What is theta 2? And what is theta 3? We said this solid is heated. If you take, for example, the case of an egg, when you eat an egg, you don't eat the egg while hot. What do? You drop the egg inside a cup of water for the egg to be cold. So before you drop the egg, the heated egg is theta 1, which is what we call the temperature of the solid. That is, theta 1 is the temperature of this solid that you heated. What is theta 2? Theta 2 is the temperature of the liquid plus the calorimeter before you dropped the solid. So it means theta 2 is temperature of liquid plus calorimeter. So what is theta 3? After you dropped the solid, which is the hot solid, inside the calorimeter and the liquid, after some time, the water here becomes warm. And that is what we call theta 3, which is the temperature of the mixture. That is the mixture of the hot solid, the liquid, and the calorimeter. So if H, which is the heat capacity, is given as this, then we can write an expression for this, since we have that the heat lost equal to heat gain. So what is losing heat? The hot solid. What is gaining heat? The liquid and the calorimeter. So to that effect, we have MC theta, that is for the heat lost, equal to MC theta plus MC theta. So since this equals this, so how do we draw a line of dichotomy between the temperatures? So to that effect, for the heat lost, we have MC theta 1 minus theta 3. Why? Because the temperature of the solid will be hotter than the resulting temperature you get after you've dropped the solid inside the liquid. So that's why this one is theta 1 minus theta 3 for the heat lost. Now for the heat gained, we have MC for water. If it is water, no. For the liquid could be any liquid, that's the liquid inside the calorimeter, into theta 3 minus theta 2. Why? Theta 3 is the temperature of the mixture, while theta 2 is the temperature before you dropped the hot solid inside the mixture of calorimeter and the liquid, plus MC for copper into theta 3 minus theta 2. And this equation is the basic equation we use for calculations. So anytime you're asked to calculate, we'll be given everything except one. Then we can get the resulting calculation that we are asked to do. So we'll take a question. We have the question, what is meant by the statement, the specific heat capacity of copper is 400 joules per kilogram per Kelvin? We come back to the definition of specific heat capacity. We said specific heat capacity of a substance is defined as the heat energy required to raise a unit mass of the substance by 1 degree Celsius. So the question states that what is meant by the statement, the specific heat capacity of copper is 400 joules per kilogram per Kelvin. So all you need to do is to go to the definition of specific heat capacity. Anywhere you have substance, then you put copper there, and that answers that. Now the second question will be written on the board. The second question is going to work basically on the principle of this equation that I've just explained. So I'll highlight the question on the board, then we'll try to solve together. So we have a piece of copper ball, a piece of copper ball of mass 20 grams at 200 degrees Celsius is placed in a copper calorimeter of mass 60 grams containing 50 grams of water at 30 degrees Celsius, full stop. Now said ignoring heat losses, find the final steady temperature. So a piece of copper ball of mass 20 grams at 200 degrees Celsius is placed in a copper calorimeter of mass 60 grams containing 50 grams of water at 30 degrees. Now said ignoring heat losses, what is the final steady temperature of the mixture? The question gives us in bracket the specific heat capacity of water as 4.2 joules per gram per Kelvin, the specific heat capacity of copper as 0.4 joules per gram per Kelvin. So since everything is in grams, we work in grams, and if you like, you can convert to kilograms. Like we said, the way out, the first way out is we write our equation that the heat lost equal to heat gain. That's the solution. We have a heat lost equal to heat gained. What is losing heat? Like the principle I explained, let's come back here. I said you have a calorimeter which is lagged, you have a stirrer, and you have a solid here, and the calorimeter has a liquid. We said when the liquid is solid, hot solid is heated and dropped here, this solid is going to lose heat. Why this calorimeter and the liquid is going to gain heat? So that's why we have heat lost equal to heat gained. So we start listing the parameters. We say the parameter that is losing heat, we say the heat lost, we have a mass of copper that is losing heat, which is 20 grams. We have the specific heat capacity of copper is given as 0.4 joules per gram per Kelvin. Then we have the initial temperature of that copper, that is the initial temperature of copper as 200 degrees Celsius. That is for the heat lost, we are true. So for the heat gain, what is gaining heat? That is, let's come back here, which is the calorimeter and the liquid. Now for this question, the liquid is water. So we write for our heat gained. Heat gained, we have a mass of copper calorimeter. We check the question. Is placed in a copper calorimeter of mass 60 grams, so that's 60 grams. The specific heat capacity of copper calorimeter is still the same, which is 0.4 joules per gram per Kelvin. Then the temperature of copper, which is 30 degrees, because copper and water are in the same place, so they are going to have the same. So like we said, for the heat gained is in two parts, that is the copper and the liquid inside the copper. So we have the mass of copper calorimeter is 60 grams, the specific heat capacity of copper is this, and the initial temperature is this. So the temperature of the liquid is the same temperature of the copper calorimeter. So we say initial temperature of copper calorimeter is 30 degrees Celsius. Now the heat gain is in two parts. That's also for the water. So we say mass of water. If we check the question, 50 grams of water, that's 50 grams. Then we said the specific heat capacity of water is given. That is the specific heat capacity, which is 4.2 joules per gram per Kelvin. Of course, the initial temperature is the same, so I don't need to write that. Please, let's note our three temperatures: theta 1, theta 2, theta 3. Like I said, theta 1 is the temperature of the solid. Theta 2 is the temperature before you drop the solid inside here. While theta 3 is the temperature you get after the solid has been here for some time. So from this question, our theta 1 is 200 degrees Celsius. Our theta 2 is 30 degrees Celsius. Our theta 3 is what we are asked to find. So we have there, we come here that mc theta equal to mc theta plus mc theta, that is the heat loss, equal to the heat gain. So we have mc theta 3 minus theta 1 equal to mc theta 3 minus theta 2 plus mc theta 3 minus theta 2. So for the heat loss, we have the parameters here, so we'll fix it in there. We'll come here, we have the parameters here, we'll fix it in there. So we have 20 times the specific heat capacity, which is 0.4, times the temperature change, which is theta 3, which is what we are looking for, minus theta 1, which is 200, equal to the heat gain, which is in two parts for the copper calorimeter and for the water. So for the copper calorimeter, we have 60 times 0.4 into theta 3 minus our theta 2, which is 30, plus for water, the mass of water is here, which is 50, so which is given as 50 times the specific heat capacity, which is 4.2, into theta 3 minus 30. So the rest is algebra. So when we expand the bracket, we have 8 into, that is when we multiply this, we have 8 into theta 3 minus 200 equal to 24 into theta 3 minus 30 plus 210 into theta 3 minus 30. So when we expand the bracket, we have 8 theta 3. We have this equal to 24 theta 3 minus 720 plus 210 theta 3 minus 6,300. So when we collect like terms, we have 8 theta 3 plus 24 theta 3 plus 210 theta 3 equal to 1,600 plus 720 plus 6,300. So we have 8 plus 24 plus 210 to give us 242 theta 3, which is equal to 8,620. So we have our theta 3 to be 8,620 over 242. So our temperature of the mixture equals 35.6 degrees Celsius. And that is the basic idea. That is the basic idea we need in specific heat capacity. For electrical heating, we have MC theta to be IVT, where I is your current, V is your voltage, and T is your time. That is for electrical heating. Also, we know that the current is the square, is the same thing as voltage over current. So if you are not, voltage over resistance. So if you are not given the current, we can do that. So when a substance changes from solid to gas, it is called sublimation. When it changes from gas to solid, it is called sublimation. So we want to proceed further to look at the specific latent heat of a substance. We say it is the heat energy required to change the unit mass of the substance from one state to another without a change in temperature, because latent heat is the same thing as hidden heat. So we have that the specific latent heat of fusion is the quantity of heat required to change the unit mass of the substance from solid to liquid state at the same temperature, while the specific latent heat of vaporization of a substance is the quantity of heat required to change the unit mass of the substance from the liquid to the vapor state at the same temperature. So that solves that, and that is the basic idea, that is the basic knowledge that is needed in our calculation. Now for latent heat, the heat lost by the calorimeter and the water is in two parts. That is the heat gained, the heat lost by the calorimeter and water is given, while the heat gained is in two stages. The heat gained in turning the substance from ice to water, then from water to vapor. So it is in two stages for latent heat of vaporization. We quickly put that on the board. So putting that on the board, we have the heat lost, which is by the calorimeter and water, as M1C1 into theta 1 minus theta 2 plus M2C2 into theta 1 minus theta 2. That is for the heat lost by calorimeter and water, while for the heat gained is in two stages. That is heat gained by ice by melting to water at 0 degrees, then heat gained by melted ice when it changes from 0 degrees to a particular temperature theta 2. So that will give us the heat lost equal to the heat gain, which this is for the heat lost, which is equal to the heat gained, which is M3, that is the heat change from the from ice to water, plus the heat required to change it from water to that particular temperature, which is theta 2. So that is the basic idea of the latent heat, and it follows suit from our previous example, and that wraps up our quantity of heat.